Well, good afternoon, everybody. Welcome at the webinar Lignin, the underutilized biopolymer. It's organized by the Lectorenplatform Biobased Economy. And I will host the first part. My name is Simon Hageman. I am Associate Professor at the Chair Sustainable Energy Systems of Saxion. And normally this Lectorenplatform is led by Jappe de Best from Advance, but he could not join us today. We start with a mini lecture of Karin Struijs about lignin. Then we continue with a presentation of lignin in practice by Sten van Lanen. And then we see Karin Struijs again with the second presentation, Research towards Properties and Application of Lignin, Connecting Fibers. And then we have 15 minutes for questions and answers. And I think we round up at 5 o'clock. But first, two messages. If you have questions, please provide them in the chat and we can handle them at the end of the session. And the presentation, the slides will be shared afterwards. Now I'll tell you briefly about the Lectorenplatform Biobased Economy. Well, the Lectorenplatform Biobased Economy is a collaboration of almost all the applied universities of the Netherlands. And you see here the map, and we are spread all over the country. Basically, we have three goals. That is stimulating the research in the field of bio-based materials and energy. We want also to create more public awareness on the theme bio-based economy, and we are looking for international and national cooperation on bio-based materials and energy. Well, we have several ways to do that, and there is a whole list of 6 points, and today we give some public awareness and on this theme on lignin. And here you see an impression of our network. In the middle we have our bio-based economy platform, and you see that it's all connected with other platforms, programs, institutes, and we have organized our research in 6 lines, and that are ingredients and components. And I think today's presentation is about ingredients and components. That was it, very short, but of course we are here for the presentation. If you want to know more about the Lectorenplatform Biobased Economy, you can follow this link and you can read it, but after 5 o'clock, of course. Then I will give the floor now to Karin.
Let me share my screen. No, I don't. Yeah. Okay. Also from my side, welcome to this webinar. It's entitled Lignin, the underutilized biopolymer. And why did I choose this title for this webinar? And that's because lignin is one of the most dominant biopolymers on Earth, but only 2% of it is applied currently, and the other 98% is incinerated or just burned. But then the question is, why is it still underutilized? And a lot of part of that answer lies in the complex chemical structure of the molecule. And that's why I want to discuss that complex chemical structure of lignin so that we better understand what's happening. But let me first introduce myself. My name is Karin Struijs and I'm a senior researcher at the Lectorenplatform Biobased Innovations. And I'm responsible for all the research in the line of the biorefinery and the analytical chemistry. Now, you probably know us better as the Han Biocenter, but actually the Han Biocenter is our center of expertise. And there we have the mission to create and contribute to a healthy environment. And now I hear that my slides are not going to the next one. So let me see does this work? Yeah, this works better. Okay, so the mission of the Han Biocenter is that we want to contribute to a healthy environment, and that healthy environment can and should be interpreted as contributing to a green and sustainable world, and that's the research topic of the Lectorenplatform Biobased Innovations. But we also have a second lectorate, which is not the topic of today, but just to mention it, and that's the Lectorenplatform Drug Discovery, where we contribute to a healthy environment by developing new medicines. So in the Lectorenplatform Biobased Innovations, we want to contribute to the development of the biobased economy by developing key enabling technologies to make new chemical building blocks, biochemical building blocks, to create new materials from residual biomass. The residual biomasses, where do you have to think of? Basically, that are materials which are often lignocellulosic, like wood or wheat straw, but also crops like miscanthus or fiber hemp. So and most of the time it are the cell wall components which are forming the biomass. And here I give you a schematic representation where you see that lignin, or the cell wall, is composed of lignin as one of the main components, but also cellulose and hemicellulose. Now, cellulose is applied a lot, for example, in the paper industry, but lignin is a residual product, still a residual product, and therefore underutilized, and therefore we need to dive a little bit deeper into its structure to see how we can make use of it better. So if you look at the structure of lignin, then here it's a schematic representation which you find all over the internet if you Google for it. But if you Google, you see many different representations. What do they have in general? They show a complex structure, and they show three different, or yeah, basically three building blocks, which are paracomaryl alcohol, the H monomer, the coniferyl alcohol, also indicated with the G monomer, and the sinapyl alcohol, the S monomer. So that's basically what everybody knows about lignin. It's complex, and we have the three monolignols where it's being built of. But if you look to the biosynthesis of lignin, lignin is being, there are several, or actually two theories about biosynthesis of lignin. One is that it's based on radical coupling, and the other one that it's enzymatic. So far, there are, the majority seem to go to the radical coupling, so that's the theory which I present with this picture. So basically what's happening is that we first need to produce the monomers. I will focus a little bit on the monomer synthesis in the next slide, but that monomer synthesis takes place intracellular, and that is enzyme controlled. So it's controlled by the metabolism of the cell. Then a second step is that those monomers need to be transported to the lignifying cells, because not all cells have a very strong lignified cell wall. The third step in the biosynthesis is that your monolignals have to be transferred over the cell wall to the outer layer where the lignin is being formed by a radical coupling process. The fact that it's radical coupling already indicates that it's a rather unpredictable process, and that's also one of the reasons why it's giving rise to such a complex structure. If we zoom into the synthesis of the monomers, then I show you here a very complex structure. And basically, why I show you is that we normally assume that there are 3 monomers, but actually there are many more. So up till now, there are about 35 monomers being identified, but still the bulk are the S, G, and H units. And those monomers are under control of the metabolism, but also those monomers also define partly the structure of the lignin. For example, if there are a lot of S units, so the synapyl alcohol units, then that leads to a lignin where the linkages between the monomers are pretty easily hydrolyzable. If you have, for example, a lot of H units, which is the case in Miscancell, where we will hear about later in the second talk, H units are very susceptible for dimer formation, which prevents chain elongation. So that are two examples of what happens when you have different monomers. But also those minor constituents can also play a role. So if you, for example, have the group which is represented over here, those are known as change starters. So they start the formation of lignin chains. So if there are a lot of those change starters, then probably the chains will be shorter. If you have compounds with 2 OH groups on the ring structure, like this one over here, then there are possibilities for cross-linking within the lignin, more cross-links, which results in a more rigid and more hydrophobic lignin. So the chemical structure of lignin is based on the monolignals, the type of monolignals, how much of each, but also the type of bonds. And over here you see that's what I just mentioned. So for example, the S units, they form a lot of beta-O4 linkages. They're easier hydrolyzable compared to, for example, the carbon-carbon linkages when you have 2 G units coupled to each other. The type of monolignals present is defined by the type of biomass. So for example, hardwoods, they contain mainly the S and the G units. Softwoods, mainly, basically only the G type, but grasses, for example, also contribute a lot of, contain a lot of the H units, and up to 33%. And that also makes sense because grasses are less rigid compared to hard and softwoods. And we just said with the previous slide that the H unit tend to stop the chain formation. So you probably have shorter chains, which result in a more flexible plant. But it's not only about the type of biomass. Also, there are large variations between individuals. So there was one publication about the Populus trichocarpa, with the balsam populier in Dutch. And there you see that dependent on the growth conditions, the lignin content can vary with a factor, can almost double. And the S to G ratio can vary from 1 to up to 3. So there it's even a 200% difference. So lignin is very complex, and it's a recalcitrant molecule, and it's based on the type of biomass, but also based on the growth conditions. It would have been nice if this is the complete story, but that isn't. So already what you see in this picture is that also processing factors like the extraction technique has an influence. And you already see that here, if you compare these two, they're both results from spruce. This one, the top one, is extracted with the organosolv method, and the spruce is extracted by the craft method. So already based on visual observations, you see that they are different. And also when you look at the chemical structures, you see that there are differences after extraction. So also the extraction procedure has an influence on how your chemical structure look like. So all these factors, so tough biomass, fluctuation, processing, and there are many more, or probably several other factors influencing the fact that lignin is such a complex and recalcitrant molecule. This is a challenge, but this also opens opportunities to create lignins with specific properties for specific applications. And when you look into literature, there are many different types of application described, but I think it's much nicer to hear about the application from one of our partners, Sten van Lanen of Miscancell, about the different applications. And just to round up, the Han Bio Center exists for almost 20 years, so we will celebrate this in January. So you're all invited to come and join us there. So Sten, I will stop sharing, so then it's up to you.
So my voice will be over the same microphone because we're sitting next to each other. And I will start my presentation. Even kijken. En dan is nou. Oh. Yeah, there it is. Okay. Wow. Myself.
Oh.
Yeah. Yeah. Sorry.
Kan je nu praten?
No, myself. Always nice.
Ja.
Oh. Sorry. Let's try again. Here we go. So a short introduction about myself. I'm Sten van Lanen. I'm a chemical biochemist. I always call myself because well, I'm a chemist in general. I did biochemistry as a master. I'm a project manager for R&D at Miscancell, and I mostly work at project towards the valorization of the cellulose and lignin after extraction of those materials. And the extraction of those materials is our main goal at Miscancell, or our main business. So what we do at Miscancell is a total valorization of miscanthus in a sustainable way, without any unusable materials. And we try to recycle all chemicals used in the extraction process. Like I said, the main products we extract are cellulose and lignin. Other extracts we tend to extract in the future are hemicellulose, xyloses, for example, and phenolics. But today I want to talk about the lignin, or the green gold, as it's called over the internet. Around 20 years ago or something, lignin was seen as an industrial burden. It was a waste. The only thing you could do with it is burning it. And a famous saying in the paper industry was, You can do anything with lignin except make money. Nowadays, it's shifted to an awakening era of lignin. It is a universal material. We already have some lignin first biorefineries, which we are not. And it's referred to as the green gold, which is strange because it's brown. To give some examples about why it's green gold, it has a lot of advantages. It's non-toxic, for example. It's a prebiotic, it's antioxidants, it's a UV filter, and the possibilities are therefore endless. Between brackets, of course. And you can see that in literature. In literature, you have a lot of nice things which you can do with the lignin. For example, you can use it as a antibacterial or drug delivery material. It's used as a biosensor and wound healing in tissue engineering. It's used as a lignin nanoparticle for example, absorptions of heavy metal. You could use it in water treatment. You could use it, for example, as a shape memory additive for polymers. You could use it in green bitumen. You could use it for everything. And it makes you a lot of money because it has a market potential of trillions and billions of dollars. So why is it then underutilized? As Karin already mentioned, only 2 to 5% is nowadays utilized and the rest is burned. And why is that? I will skip a little bit over this because it's an overlap with the last presentation. It's a very recalcitrant molecule, which already was explained. It is complex. It is irregular in structure, so it's kind of hard to work with. And it is a broad concept of the same molecule. So one lignin is not the same as another lignin, which was also mentioned already. That has a lot of influences, as you can see on the right hand side. Not only the feedstock changes the lignin, but also the processing type, process conditions, the post-processing methods all change the lignin in a way which are sometimes a little bit challenging to work with. And as you can see on top on the right hand side, this is an example, sort of the same example that was just given about the one type of lignin or one type of feedstock for the lignin with different extraction processes which give different types of lignin and different molecular structures. So one of the challenges of using lignin are the types of lignin, as I already mentioned. And why is that? That is because one lignin could yield very different properties compared to other lignins. For example, a melting behavior or a solvation properties of the lignin itself. So one dissolves in one solvent and not in the other. So one lignin could work for your application while another will not. Furthermore, the purity and the consistency of the lignin can change between types, and the availability, depending on its type, could also be a challenge to work with. And the expectation is then often, if people worked with lignin before, they say, well, this one worked, so all will work, or this one did not work, so all will not work. And they expect often that it works as is, which is mostly not the case. So you need a little or an additive or a modification or fractionation for a good application. So knowledge of lignin properties of the various types of lignin is important, and especially for the various applications you want to apply it to. So what do you need, etc. At Miscancell, we get positive as well as negative feedback on our lignin, mostly positive, of course. But one of the things, for example, is that our lignin is more reactive than wood lignin, which is a positive thing for most of the applications. But another negative thing could be, for example, that we don't have an obvious melting behavior as, for example, a kraft lignin does have. Another challenge is the chemical structure, as already explained a little bit. So the monomeric composition is mostly dependent on the plant species, but could also depend on the extraction method or the processing method. And those are the S, G, and H monolignals, which were already talked about. But the extraction method also greatly influenced the chemical structure, as you can see on the downside of the screen. Different extraction methods give, for example, different sulfur content or phenolic hydroxyl content or methoxy content. And it also influenced the macro properties like the purity, which is the ash content, for example. But the chemical structure influences also other properties of the lignin. And well, the molecular weight, of course, a little bit of a chemical structure, but it's pretty important in most of the applications. And at Miscancell, we use sort of an alkali lignin. It's not exactly the same as an alkali lignin, so it's a little bit different again. It is mostly comparable to alkali lignin, but we have our own patented extraction process for miscanthus, which is a little bit different than, for example, for wood. As you can see here, the alkali lignin has a pretty high molecular weight compared to other extraction methods. As said, the miscanthus has a little bit smaller molecular weight than wood, but due to the extraction process, our lignin is pretty high in molecular weight, which gives its own properties. So to conclude it and to put it in simple words, why is lignin underutilized? That's mostly because it's so diverse and not well understood in general. It's not well defined or standardized. It is a very hard molecule to work with. It doesn't do what you want. Well, if you know how to work with it, it does, but and it's not a one-size-fits-all molecule. Therefore, in my opinion, knowledge about lignin in general is key. Standardization for several types of lignin is key, and a stable supply is also key. But to give an example, a stable supply requires a stable demand. That requires a good application to have a demand for that lignin. That requires knowledge about the lignin and the application. That requires standardized material. That requires stable supply, and that requires stable demands, and etc., etc. So to talk about Miscancell and our possible applications and projects, we are working with a lot of partners, and most projects we do not research ourselves, but we just are lignin suppliers. And most projects are in research stage or in early research stage. There are various post-processing techniques which I would not elaborate, but those techniques yield various possible applications, as Karin said at the beginning of her first presentation. It's also an opportunity to use it in different ways. So, for example, you can use lignin as is in asphalt, which is already commercially available, or as a natural binder. For us, it works a little bit less as a natural binder, but I think you will talk about it later on.
Slightly.
If it is modified or fractionated, I put them together. It's not the same, but I put them together. You could use it as a natural binder. You could change the properties of the lignin a little bit. So it has more reactivity, and you can use that as polyphenol, for example. And if you degrade it to monomers or small chemicals, you could use it as an aromatic building blocks, for example. One of the applications, or one of the projects and applications we are working on at Miscancell, and I am working on actually, is the usage of lignin as a natural thermoplastic polymer, and then our idea was to put it in a fiber board as a binder. As you can see on the right, we tested a lot of different. This is all our own lignin, but we tested a lot of different fractionation methods, and the rest, the right side is blocked a little bit. Those are modification methods. I don't want to go in there, and I don't want to disclose everything, so that's why it's blurred. We chose one of the fractionation methods, which is a liquid fractionation, and you can see at the arrow point it dropped the TG below 100 degrees, and you could see melting behavior below 180 degrees. So we made a board of it, and it looked actually pretty good. It was soluble. However, if you look at the right down hand side, you could see that the board did not meet the standard stiffness and strength properties. It is a start, but it's for a board. It's not yet there. Another project, which I already mentioned and which is more of a success story, is our grasveld. We use the lignin as is in the grasveld with some green additives if necessary. So no modification or fractionation is necessary. But if you modify the lignin slightly, you could enhance the amount of lignin which you could add to the asphalt mixture, and the properties could be a little bit enhanced of the overall asphalt mixture. As I said, it's already applicable, it's already available. We already have 100,000 square meter of grasveld in the Netherlands and Belgium, and it looks good over the years. And you have a few advantages of lignin if you use it in asphalt. For example, it has antioxidative properties, and it improves the service life of the asphalt. So this is for us the one application which we already which is already commercially available, and the rest is still in research. So with that, I wanted to conclude my part of this seminar. So thank you for your interest.
Yeah, thank you.
Yep.
So during the last talk, I would now I see whether it starts sharing properly. Yes. So during this last talk, I would like to tell you something about one of our research projects, which we do towards the application of lignin, and it's called Connecting Fibers. Before I come to the project, I want to just put it in perspective, because this slide I showed you before, but it shows again the aim of our lectorator or research group, and it's that we want to develop the key enabling technologies, and I will show you some technologies we are investigating, and to make bio-based chemical building blocks and materials from residual biomass. And basically our dot on the horizon is that we want to go to a zero waste situation. And that's why the biorefinery comes into place. So biorefinery is basically a toolbox, a collection of all kinds of technologies which can be used to fractionate biomass into its ingredients. And later on, those ingredients can be turned into marketable products. So we can for the biomasses we use there, we can use the lignocellulosic materials, but we can also use residual side streams from, for example, the fermentation technology. So there we link the different research lines from the lectorate to each other. Within biorefinery, it's about the separation of the different biomasses, and the term biorefinery is related to or is derived from the oil refinery, with this difference that the molecules present in biomasses are much more complex and much more diverse. So you also need a broader toolbox to obtain all the different kind of molecules. In this, as part of our biorefinery research line, we started a project which is called Connecting Fibers, where we try to find an application for lignin. And this project is based on several questions from our network. But I think one of our partners stated, like, how cool would it be if we can use the side streams, so for example the sawdust or small branches of our feedstock, of our biomass, to create a resin by which we can glue our biomass together. So for example, from bamboo you can make bamboo poles or bamboo planks, and if you can glue them together with a glue coming from bamboo. So this was basically the start of this project. So we aim to use the lignocellulosic materials from our partners. So that's bamboo, Miscancell, of course, fiber hemp, and pruning wood. And we want to turn it into an adhesive or binder and to produce it as into a panel board. And at panel board, we opted to go for CLT, so that's cross-laminated timber, because that's a type of material which can be used really as construction purposes. For the type of binder, we opted to replace also a binder which is currently used in the production of CLT, which is a PF, phenol formaldehyde resin. And this is a purely non-bio-based resin, so it's based on fossil sources. Formaldehyde also, and both formaldehyde and phenol are also rather toxic compounds. So we thought it was a good idea to try to find a bio-based alternative for it, to make 100% bio-based CLT. And lignin seems to be a very good candidate to replace phenol, since lignin is one of the few or only compounds, biomolecules on Earth, which already consist the same ring structure as also is present in phenol. Second step, we want to replace formaldehyde by glyoxal. Glyoxal is dialdehyde, less reactive compared to formaldehyde, so therefore less toxic. And so in theory, and also according to a publication of Shikimori, it should be possible to prepare a lignin glyoxal resin. But as Sten already mentioned, what works with one lignin doesn't necessarily work with another type of lignin. So the aim of this project is to develop the bio-based resin. And we separated the project into 3 work packages. And the first work package is about the extraction of lignin from different types of biomass. So this is really about the development of the key enabling technologies to obtain proper lignin. Second is about the synthesis of the resin. And the third work package is about the application. So so then the research question of the first work package is which extraction methods is most suitable to extract lignin. And here it's an overview from different extraction methods. We ruled out the mechanical ones because there you still end up with a mixture of lignin and cellulose. From the chemical ones, the other ones are in a rather preliminary state, so we hope we can use them in future research. So therefore, we ended up with the sulfur process and the sulfur-free process. Now, the kraft lignin we used as a reference because that's pretty well commercially available. We didn't make kraft lignin ourselves because of the safety reasons of the sodium sulfate, which is involved in there. But we did compare the soda and the organosulf extraction methods. So we want to compare those two methods, organosulf and soda, and basically they differ in the type of extraction solvent, but they also differ in the way the lignin is recovered. In case of the soda extraction, we precipitate the lignin by adding acid, and in the organosulf, we simply can evaporate the ethanol. But it's not only the extraction process we are interested in. We also have reasons to believe that the extraction parameters, so the exact conditions, will also have an influence on the exact properties of the lignin being extracted. So that's why for the soda extraction procedure, we made a design of experiment approach. So for those of you who are not familiar, the DOE is a method to pretty quickly, without having to test all combinations, get an idea of the effect of a couple of parameters and how they interact. And then a statistical model is being created based on the data set. So we designed a DOE for the soda extraction procedure, in which we varied with the temperature, the extraction temperature, so from 90 to 170 degrees, and the molarity of the sodium hydroxide from about 1 till 7.5 molars. We analyzed them based on the yield. We measured the molecular weight distribution, and we analyzed the monolectinal composition. In this talk, I will only show you some results of the yield we have obtained. And if we first look at some results where we compare the two different extraction methods, then on the left-hand side, you see the result of the soda extraction, and on the right-hand side, the organosulf. And so the temperature is on the y-axis, and the sodium hydroxide or ethanol concentration is on the x-axis. What's really clear from this figure is that the yield obtained with the soda extraction is much higher compared to the organosulf. And I think for now that's the most important take-home message, that there are really clear differences in this case already, the yield which is being obtained. By the way, based on literature, the lignin content is about somewhere between 20 and 30% theoretically. So we do extract about 50% of the theoretically maximum, but that's probably also to do with the scale we perform the experiment on. So we know already that we lose some lignin in our extraction method. So then if we look to the effect of the different parameters, and here you see the DOE results of bamboo instead of miscanthus. And what you nicely see here is that the higher the temperature, the more lignin is being extracted. But for sodium hydroxide concentration, we should be somewhere in the middle, around 4 to 5 molar. Then if we look at the results from the model, then the NOH concentrations, they pretty fit well inside the box. So that's the reliable part of the model. But you see the predicted temperature where the optimum extraction temperature would lie, they all lie outside of the box. And that means that actually that temperature, the maximum of extraction temperature cannot be predicted in a reliable way. And yeah, then I also ask myself the question why it's not reliable, and that has probably to do, or why it lies outside of the box, and that has probably to do with the fact that we choose our variables based on literature, and it's practically almost impossible to go to much higher temperatures compared to the temperatures tested. So we can maybe go to 200 degrees, but when you go much higher than the pressure which is being built up, it's too high to be able to perform the extractions in a safe way. So we did some analysis already for the molecular weight distribution, and we definitely saw differences there between the different feedstocks, but also different extraction parameters. But we still have to analyze all those results. So the second part, the second work package is about the synthesis of the resin. So this is just, and I will go a little bit quicker now because of the time. This is the procedure, and this is the procedure derived from literature. And basically what we do is we make combinations of lignin and, let's say, glycol or phenol formaldehyde. We first heat it to form dimers, and dimers is one phenolic compound which link with one of the linker, the aldehydes. Then we heat it up a little bit further to create the resin, and then we need to formulate it to be able to measure this, for example, the tensile strength, so the actual output parameter. So we started to repeat the procedure which was described in literature, but that was not successful, and that's probably to do with the type of lignin we had. But also, since in the previous slide I showed you the whole procedure, and we started at the beginning and we could only measure at the end. So there also we had a lack of, let's say, a reference compound, and that in the Netherlands there's not a reference PF being available. So therefore we decided to make it ourselves, and that worked pretty well. So we are capable to make the resins. Making a phenol glycol resin, on the other hand, as a next step, was not successful. And to our surprise, there was also basically no literature available about that. And that brought us to the conclusion that probably it's very hard to make a phenol glycol resin. So then we opted to first try to make a lignin formaldehyde resin, and that works well. And here in this bar graph, you see some of the results of it. And basically what we're currently testing is all the different parameters. Over here, you see different ratios of the lignin and the formaldehyde. And you see, especially with the last ratio, that we are coming pretty close to the properties also of the traditional PF resin. So also there we are continuing. And then the last step in the process is that we want to test the properties, or we want to go towards the application. So what we intend to do is make a resin, a lignin formaldehyde resin, from different types of lignin, so from the different sources, but also probably different extraction methods, and to really see whether they have different properties while applying them. And we are also interested in other type of questions like, are there differences in how the different lignins interact with the different types of wood? So we just started this work package, so I hope we have still another half a year left in the project, so I hope that we can make some steps in that direction as well. So basically I want to end up this presentation with a few take-home messages. So the extraction method influences the properties of the lignin. What I didn't discuss, but which is good to remember, is that the analysis of lignin is also a challenge. We have been developing a method to determine the molecular weight distribution, but for that will be presenting in another way. And I'm very happy that we managed to create already a lignin-based resin. So yeah, for the we wouldn't be able to do this research without the funding from SIA. So thanks for that. Special thanks to our partners, but I couldn't do this, or we couldn't run the project without my closest colleagues, Else Kracht-Piret, Sarah Reisma, and our master's student, Koen Bussink, and of course, all other colleagues and students which are part of the project and giving us mental support. So yeah, if you want to know more, please register for our the symposium on the occasion of our 20th anniversary. So thanks for listening, and if there are questions, this is now the floor is open for that.
Okay, thank you very much for the presentations. Questions can be, if you have questions, put them in the chat. And there are already 2 questions. I will start with a question for you, Karin, because this is about the last presentation. And one of the questions is from Martijn Sieverink, and he asks if there are any bio-based routes towards glyoxal.
Yes, there are, but we haven't studied them. So just a quick...
Okay, yeah, but you can have more contact after this webinar. Then another question.
So we started this project basically from scratch, so we decided to focus on the extraction of the lignin, to obtain different types of lignin and to apply the lignin. So to replace the formaldehyde or the glyoxal, that was not the focus of this project. But there are still many questions open.
Okay, then I still stay with you because another question appeared. What do you mean by saying the reaction with glyoxal was not successful? Was there no reaction at all?
So phenol glyoxal, yes, there was a reaction, but that didn't lead to a resin. So what we saw that let's say, yeah. So since this was still, let's say, the monomeric units and the small, so not lignin based, we could do some LCMS analysis, and there we saw that one phenol could react with one glyoxal, and we saw different variations there, but we didn't see any further polymerization. And that's what you need to go to a resin.
Okay. Then I have a question for Sten. But this question appeared halfway your presentation, and then you showed us 2 examples, so maybe it's partly answered already. The question is, who are your customers? What applications do they use your lignin in, and what properties are they looking for? So yeah,
that's very diverse, as I try to explain. We have different kind of customers. Most of them are researching ways to utilize lignin in their products to maybe search for an alternative for example, as Karin said, phenols. But also, as for example, in sunblock for UV blockers, or what else do you have? For example, the carbon fiber, or in batteries, we also have some people that are looking into that. So it's very diverse. I cannot disclose everything, but the two examples which I got into are our own research, and so that research is mostly done by ourselves.
Okay. And at the moment, Sten, what are currently the main bottlenecks to get to a new application for the Miscancell lignin?
Well, workability with the lignin is a big thing. So how do you apply the lignin? Does it dissolve in certain solvents which you use in your process, for example, for different things? Another is also availability. We are still small. We are setting up a demo plant, a big plant to extract, I don't know how many tons of lignin per year, but 100 tons around that figure. So availability is one of the key things, and of course price. If you want to modify or otherwise change your lignin, that's gonna add up to the price. But for some applications, that is still in the right range. So yeah, for us, for our lignin, it's mostly availability, I guess. And for the asphalt lignin, yeah, we have available lignin, so that's a different story.
Okay, thank you. Then there is a question about again about the process, Karin. Are you going to continue the formaldehyde-free route, so without the formaldehyde?
I hope so. So currently we're trying to get the process let's say in our fingers, so that we know which parameters do have a big influence, which have less influence. And when we have that knowledge, we hope to make the next step and go to the formaldehyde free and replace the formaldehyde by the glyoxal. But everything depends a little bit on the actual results we're obtaining. And as I just mentioned, the time we still have available in the project is just a couple of months. So we have to see where we come. So the intention is there. If we reach that point, the future will tell.
Okay. Then some questions about the process. You use an extraction method. And is this a single step extraction, or is it more like a repeated step? What do you use in your experiments?
So in the experiments, it's a single extraction. But we did also test it if we do subsequent extraction. And then, of course, you see the same trend as with normal extractions, that the first round you obtain about 75% of all the yield of the lignins, and then the second step it's 10-15%, and then the last couple of percent with the third extraction step. We didn't go any further than 3 extraction steps. What we didn't do is do the calculations and to see whether it's worth to do 3 subsequent extractions or just keep it by 1 extraction step. So whether the additional cost to obtain a higher yield make up for the benefits of obtaining a higher yield. But that also depends on the prices of the lignin and so on. And since they are fluctuating a lot, I think we now know how it behaves, and then based on that, for example, Miscancell can decide whether they want to do a single extraction or multiple extractions.
Okay. Then you showed us it is a very complex molecule, the lignin, and it's a very complex process. I saw sodium, I saw high temperatures. In what way do you say the products are bio-based because of the use of all the other chemicals? Can you say something about that? Maybe also Sten.
Yeah, so the other chemicals for extraction will not is maybe too much to say, but they should not end up in the final product. And for our extraction process, we have a method that recycles all the chemicals used in the process, in the extraction process, to regenerate them, and we can regenerate them. And I'm not I'm not the chemical technologist, but I think it's up to 96% of regeneration of the chemicals or something like that. So it's a very small amount of waste, of chemical waste, and the chemicals which we use are not that harmful. So sodium hydroxide, in my opinion, is not the worst chemical you can use.
No, and
yeah,
I agree. And especially in the organosolve method, it's ethanol, which also can be produced in a bio-based way. And recycled. Yeah, I'm also, to make the process even more green, I am considering whether we would like to explore and develop also into the more green extraction solvents like the NADES or the natural dipeptidec solvents, which is the next step towards 100% bio-based, also 100% bio-based process. So because the product is bio-based, definitely bio-based, the process part dependent on the exact method.
And generating other types of lignin with the DES again.
Yeah.
Okay, thank you very much. I think we will keep it for now as it is. People can contact you both for more questions. I enjoyed it very much, the presentations and the subject. So we will see each other around for sure. Again, thank you very much and have a good day all.
You too.